Have you ever tried solving challenging problems, but whatever you do, nothing actually works? Well, I can help you. My name is Satvik Kolar, and welcome to my YouTube channel. Hello, everybody. Hope y'all are all doing well. If you don't know me, my name is Satvik Kolar. Also, you can call me Satvik, Satvik the Magnificent, or even Sat the Great, whatever you wish. Today, I'm doing a Chemistry 1 test review for the upcoming Chapter 12 test on equilibrium. If you have any other questions, please let me know. Make sure that you hit the subscribe button, smash that like button, and turn on notifications so that you never ever miss a video again. Okay, so let's begin with this first problem here. Here, we're given the initial, we're given a reaction right here, and then we're given that the initial values are as follows. B is 0.13, C is 0.091, and D is 0.24. So what we're being asked is to just determine the direction. So what this means is it either left, is it right, or does nothing happen, so no change? So we're given here at this initial reaction, right? Which means that all we really have to do is just plug it in. So we see that B is 0.13, so, and then C is 0.091, and D is 0.24. So the first thing that we would want to do is 0.091 squared times 0.24. How this works is the coefficient here becomes the exponent, and since D didn't have any coefficient, which it just means that it's 1. So right here it's just to the power of 1. And then all of that divided by the B value, which is 0.13. Here, let's just quickly compute this. 0.091 times 0.091 times 0.24, all divided by 0.13, which gets us a value of around 0.015, and then it'd be 2 sig figs, because all of them have 2 sig figs, so just 0.015. This value of 0.015 appears to be greater than the Kc value of 0.0113. This is Q, this is Kc. So because Q is greater, that means that in the reaction it's shifting from the product side over to the reactant side, which simply means that the reaction is shifting to the left. So the answer here that we would be writing is to the left. Just a quick review over this. If QC is greater than KC, that means that it's as products to reactants. If QC is less than KC, that means that it's reactants to products. And you find if it's greater or less than by just simply putting it into plugging in those values there. Now moving on, we have a problem involving shifting between the forms of Kp and Kc. For these types of problems, we have to remember the following equation, which is that Kp is equal to Kc times R, which is given, times temperature to the power of delta N. And then R is given as 0.08206. It's important that we use this value because this is used for pressures or just gases, as is seen in the ideal gas law. We use this value. Okay. Next, what we have to do is we have to look at the coefficients of each term in this reaction and see what exactly is happening. So first off, we can see that in the reaction, every single coefficient is being halved. For example, 2 and 2a is being halved to just 1 and 1a, or c is being halved to just 1 over 2c. What this means is that the reaction is obviously being halved. The coefficients are being halved. Also, additionally, we can see that the reaction is being flipped, as the A is on the reactant side over here, but then it's on the product side over here. So what do we now do with this information? We're given that the Kp p-value is 0.665 for this initial reaction over here. But now for this new reaction, we use this value, and our first step right here would be to flip the 0.665. So it would just be 1 over 0.665. As well as we see that since the values are being halved, we do to the power of 1 over 2. If the values, for instance, were being doubled, where b becomes 2b and then 2d becomes 4d, then we would do to the power of 2. So you're just basically doing the x to the power or the exponent of whatever is happening. So in this case, it'd be to the power of 1 over 2 because the coefficients are being halved or times 1 over 2. So we can now just plug this into our calculator over here. 1 over 0.665 to the power of, and now make sure that you use your parentheses here for the 1 over 2, otherwise you're going to get a different value. And this comes out to approximately 1.23, and then it'd be 3 sig figs. Now what do we do with this value? It's actually very simple, where we just plug this value in to the Kp, because this is the new Kp value that we got. So it'd be 1.23 is equal to Kc, which is what we're solving for, times R, which is given as 0.0826, times the temperature, which is given as 444 Kelvin, to the power of delta N. Before we move on to the delta N part, it's important to note that this 444, or the temperature, has to always be in degrees Kelvin. If you use a different value for such as Celsius or Fahrenheit, you're going to get a different answer. We have to use Kelvin because in this ideal gas constant right here, it uses Kelvin. Okay, now what does delta N actually mean? Delta N is just the difference between the coefficients or the number of moles between the products and the reactants. We have to always use this final reaction or this other, the bottom reaction that's given here. Okay, so let's first look at the product side. What is here? We see that there's one gas, one solid, and then another gas. It's important to note that we only use gases. If there's a solid or if there's a liquid, we just have to disregard them as they're not important right now. So for finding the delta moles or delta N change in moles, we only use gases. So on the product side, we see an A, which is a 1, so it'd be 1, and then we see a 1 over 2, which is a half, so plus 1 over 2. That's the products, all minus the reactants. In this case, there's only one reactant, which is the A over here, which is just 1, so minus 1. This is just 1.5 minus 1, which is just equal to 1 over 2, or half. So delta N in this case would be 1 over 2. Next, we're just simply solving for what Kc is. So I'm just going to move that down here. We can plug all of this into our calculator right here and just do 0.08206 times 444 to the power of, and again, make sure you use your parentheses, to the power of 1 over 2. Oops, 1 over 2. This gets us a value of 6.04 Kc, and then that's equal to 1.23. And then it's again 3 sig figs because of this 444. Then all we have to do is simply divide to solve for Kc, where we do 1.23 divided by 6.04, which gets us a value of about 0.204, which would be our final answer here, and we are using 3 sig figs again. And then it's the value is Kc. It's a Kc value, so there are not exactly any units for it. It's just a constant. 0.204 would be our final answer for Kc. Awesome sauce. Now this following problem right here asks to write the equilibrium expression for the following reaction based on concentration. This is a very straightforward problem. And similar to the last problem, when writing the expressions, we always disregard the liquids. So this liquid right here will basically be irrelevant to our expression. Okay, Again, we follow the same exact ideas of the products all over the reactants. Or so in this case, these are the reactants, and then on the right hand side are the products. And what exactly are you putting on the right or on the numerator, on the denominator? These are the products on the numerator, reactants on the denominator. Simple. So the first value that we see here is 16 CO2 gaseous. So we would just write CO2, and then the coefficient here would just turn into an exponent, so to the power of 16. Then our next value is 18 H2O gaseous. It's a gaseous, so yes, that's okay to use. So we do H2O to the power of 18 because that's our coefficient. Now we divide all by the reactants. We see here this is a liquid, 2CH18, so we disregard it because it's a liquid. Next one here is 25 O2 gaseous. Since this is a gaseous, this is fine to use. So we do O2 and then to the power of 25 because we turn that coefficient into an exponent. So this simply would be our answer to find the expression. Pretty straightforward. It's just remembering the idea of not using liquids or solids and only using gases, as well as following the idea of products divided by the reactants. Okay, moving on, we have a problem here involving pressure in ice. We're given the initial pressures in the reaction, and then we're asked to find the equilibrium pressure. We're also given that the Kc value is 0.0103 at 615 degrees Kelvin. How do we begin this problem? The first step would be to remember the equation Kp is equal to Kc times RT to the power of delta N. And we have to just solve for Kp because this is a pressure problem and we're given the values in Kc. So it'd be Kp is equal to Kc, which is given as 0.0103 times R, which would be given as 0.08206 times temperature, which we're luckily given in Kelvin. Remember that it has to be in Kelvin, then delta N. Here, delta N is equal to, remember, the product side, which would be here, minus the reactant sides, so here and here. And every value here in this expression is given as in a gaseous state, so all of the values here are valid. So since there's no coefficients, each one of these terms has a technical coefficient of 1. So on the product side, we only have one value, so it'd be 1, minus on the reactant side, which is 2. So minus 2, which is just equal to negative 1 as delta N. So negative 1. Here we can solve for Kp using our calculator, and then it'd be 0.0103 times 0.08206 times 615 to the power of negative 1. And then we got our Kp value as a 0.0000204. And then it would be 3 sig figs. Okay, now what we have to do as our step 2 is compare this Kp value of 0.000204 to our Q. How exactly do we get this Q? We would do Qp, because it's in pressure, is equal to the product side, which is given right here as 0.33, so 0.33 divided by now the two reactants. So 8.33 times 12.85. And then we have to go back into our calculator right here, and then we see that 0.33 divided by 8.33 times 12.85 gets us a value of 0.509 or 51 because of just only 2 sig figs. this value of 0.51 is significantly greater than our Kp value of 0.000204, which means that since Q is greater than K, it means that the reaction goes from the product side to the reactant side. So now we know that the direction of this reaction would be towards the left. And we got this again by simply finding what Q is and comparing that value to our Kp value. Again, we got a value in Qp, so we need to compare this to a Kp. We don't convert it to the compare it to the Kc because that's a concentration value, which is significantly different than a pressure value. Okay, now we have to follow the ice method. So we put a C there, and we know that the reaction is going to the left, which means that this would be losing an x, this would be gaining an x, and gaining an x. And then this would just be 8.33 plus x, 12.85 plus x, and then 0.33 minus x. And again, these are gaining x's because the reaction is going towards the reactants, and these are losing an x because the reaction is, again, moving towards the reactants. Okay, now what do? Step 3. We have to use our Kp value of 0.000204, which is Kp, is equal to now our expression here. So it'd be 0.33 minus x all over 8.33 plus x times 12.85 plus x. And then now this is going to take a while. We have to just put this into our calculator here. And I'm unable to show this on the iPad here, but what we do is on a TI-84 calculator, we go into math, and then you just press the top arrow once until you see in C, it's called the numeric solver. You click on that, and then you're given here as E1 and E2. In the E1 section, you would enter 0.000204, and then in the E2 section, you would just enter what's given here on the right. So I'll just go ahead and do that, 0.000204, and then on the right would be 0.33 minus x divided by 8.33 plus x times 12.85 plus x. Then we would have to set x equal to 0 on the calculator, and then it comes out with an x value of about 0.30 or about 0.31. Okay, now what do we do with this x value? We first have to, all we have to do simply is just plug it in. So we see here on the left that the Cl2 E is 8.33 plus x. So what would we do? 8.33 plus the x value that we just got as 0.31. This gives us a value of about 8.64. This would be our PCl2. Next, we see here that the PCl3 value is 12.85 plus x, so it would just be 12.85 plus our 0.31. Then I'll just put this into the calculator. So 12.85 plus 0.31 gets us a value of about 13.16. So this would be our PCl3 value. And then also it's an ATM. I have to mention that. And then lastly, I want you guys to try this. if we're given the E value for PCl5 as 0.33 minus X, it would simply be 0.33 minus 0.31, which would get us, as you guys probably must have gotten, 0.02 ATM as the value for PCl5. Some key takeaways from this specific problem is that you have to always remember to convert Kc to Kp or vice versa when solving with these type of problems that involve the concentration equilibrium constant as well as the pressure equilibrium constant. And then through converting, we have to remember the equation Kp is equal to Kc times RT to the power of delta N, where T is always going to be in degrees Kelvin. And then remember that because we have a value of Kp, we have to always compare this value with a Qp value, not a Qc, because this is, again, using pressures, not concentrations. Okay, next we're given a problem which involves KSP, where it's given that the KSP of Li3PO4 is 3.20 times 10 to the power of negative 9, and then we're given the moles of the various ions. These moles of the ions are added to water to make a 2.00 liter solution, and we're asked to find the concentrations of the ions at equilibrium. Okay, so how I first like to begin this problem is by writing out the reaction. So we're given that Li3PO4, which is a solid, breaks up into ions. This is an ionic reaction where the compound breaks up into separate ions, hence why we use KSP, which just stands for the equilibrium value for solubility product, which is what SP stands for. Goes to the ions, which for the lithium ion would be 3Li positive, and because it's Li3, the coefficient becomes 3. And then it's positive because that's just what lithium is. It has a charge of +1. And then this would be aqueous plus the phosphates, which is PO4 minus 3, aqueous. And we know that phosphate has a charge of -3. And just to make sure the math checks out, we see here that it's a 3 and a plus, so just be a value of +3. And then a -3, and then a 1, which is invisible, becomes a value of -3. And +3 minus 3 equals to 0, which it's supposed to. Okay, how exactly do we proceed from here? What I like to do is convert these millimolars that are given into millimoles that are given into molars. And we can use this formula here that molar is equal to moles divided by liters. Again, molar is equal to moles divided by liters. First, we're given for the lithium ions that 84.2 millimoles are added. We can convert the millimoles to moles by just dividing. So that would get us 0.0842 moles. And then this value of 0.0842 can just be divided by the total solution liters, which is 2.00 liters, and that's moles, to get you around 0.0842 divided by 2, 0.0421, and it'd be 3 sig figs, and this is in molars. Following the similar logic here, we're given 22.0 millimoles for the phosphate, divided by 1,000 to convert it to the moles, gets you 0.0220 moles. And then we divide this value of 0.0220 moles by the total liters, which are given here is 2, to get you around 0.0110 molars. Again, it should be in 3 sig figs. Okay. Now, how do we proceed? We're given these molars as the initial molars, and we can just simply follow the ICE problems. So by just writing out neatly here, I would be 0.0421 molars. Here would be 0.0110 molars. And then this is a solid, so it doesn't have the value. Next, for this C, we have to find what direction is the reaction actually going towards. So I'm just going to erase these over here to give me some more room. And again, we have to follow the idea of the products divided by the reactants. Okay. So following this idea, it would just be 0.0421 times 0.0110, and there's no reactants here. So this would, and then it'd be to the power of 3, because the coefficient here is 3, and then phosphate doesn't have any coefficient. So if we go into our calculator here, we see 0.0421 to the power of 3 times 0.011, which gets us a very, very small value here, which can also just be written as 8.2, on my other calculator is given as 8.21 times 10 to the power of -7. This is a value that you should get on your TI-84 calculator. Okay, now this 8.21 times 10 to the power of -7 is our QC value, and it's C because it's concentrations. This value here is greater, QSP. This value is greater than the KSP value, which is 3.20 times 10 to the power of -9. What does this mean? Because it's greater, that means that it moves from the products to the reactants. Because now we know that it moves from the products to the reactants, we can, I'm just going to move this down here as well. We know that the C would be minus x, minus 3x, and then minus x. And then our E in this ICE method is 0.0421 minus 3x, and then 0.0110 minus x. Next, we have to go into our TI-84 calculator, again going to the numerical solver, and we have to do our KSP value, which is 3.20 times 10 to the power of -9 is equal to our reaction here, which is 0.0421 minus 3x, and then we cube it because we're given here the coefficient is 3, and that would mean that it's also to the power of 3, so we cube that, times the phosphate ions, 1, which is 0.0110 minus x. Okay. Next, we just go into a numerical solver, where on the left side, it would be 3.20 times 10 to the power of -9. And then on the right side, it'd be 0.0421 minus 3x cubed. Make sure you have your parentheses, times 0.0110 minus x. So we have to set our x equal to 0, and then we get an x value of about 0.00962, and it should be 3 sig figs, because these are all technically 3. Okay, now all we have to do is plug this x value right here into our e's. So into this and then into this to try and find the final molars, or the equilibrium molars, the concentrations. Okay, so for the lithium ions, it would be 0.0421 minus 3 times 0.00962. Going into our calculator here, it would just be, again, 0.0421 minus 3 times 0.00962, which gets us a value of about 0.0132, and it would be 3 sig figs. Now, following a similar idea here, we would do for the phosphate ions 0.011 0 minus x, 0.0110 minus our x, which is 0.00962, which gets us a value of about 0.00138, and it'd be 3SF, which means that our final values would be Li plus EQ is equal to 0.0132 molars, and then PO4 minus 3 EQ is equal to 0.00138 molars. These would be the final molars that are achieved when the concentrations are at equilibrium. Okay, I hope this was helpful for you guys, and please consider liking this video and subscribing to the YouTube channel, and please let me know again if you guys have any more questions. I'm Satvik Kolar, and I'm out.